So, based on what we did in the last class, we will now get into the concept of cryptography, and in terms of cryptography, the definition or the description is given from various dictionaries. For example, Merriam-Webster dictionary, cryptography means the coding and decoding of secret messages. Nobody else can read. For example, cryptography I write in a way that you cannot understand. That is sort of like the dictionary definition, and we can represent it as a way in which we are not able to understand what is being sent or discussed about unless it is looked at in a proper way. So, cryptography can be coded in such a way that nobody else except the way other people can look at it. So, the basic idea is to modify a message so as to make it unintelligible to anyone but the intended recipient. That is the main idea. So, for example, you have a plain text message M, which is going to be encrypted in such a way that unless it is decrypted, you cannot understand what the message is. So, that is the basic idea behind cryptography. So, in this process, the idea is to have a way to do this process. So, you need some keys, and once you have the keys which can be distributed, only those who have the keys will be able to understand the message. So, the principle is this: K, for example, is the key. The key is known only to the sender and the receiver, and that is how it is a secret. Okay. Anyone who knows the key can decrypt the message. So, the first problem in this field is therefore the idea of key distribution, because you want to actually distribute the key in a way so that it is only for the intended receiver and no one else. That is the main idea behind this. So, perfect secrecy and is roughly provided when the key that you are going to use is only going to be for once, or in other words, it is called the one time pad. So, there this is known as the perfect encrypto system, because whatever you are using, for example, is the case which is a one time pad only. If anything happens more than once, it will not be seen. The problem of distributing the keys in the first place, however, will still remain, because no matter what you do, this one time pad also has to be provided appropriately to the right person. So, the distribution of key remains as one of the most important parameters in this. Okay. So, we use quantum key distribution as one of the best ways of doing key distribution, because the quantum key distribution process is done in such a way that the distribution of the keys will be in perfect secrecy. So, the perfect crypto system essentially requires therefore a quantum computing which can utilize the quantum key distribution and one time pad. Once you have that, then you have a perfect success in terms of secrecy. So, that is the reason why quantum key distribution and that has become very powerful. So, what is the key idea from the quantum world? First is the measurement part, which we have read. The idea of observing or measurement, which we have done in a quantum way, will alter its states, which means that whenever we use a quantum way of doing our measurement, then it is only one time use. So, that is our principle of getting our one time pad in some sense. So, in this regard, the qubit, when it is observed, the state of the qubit will collapse to either one of the two states, but unless it is measured, it will be either in one of the two combination states. So, one example which is very popular in this case is the case of photons. Why? Because photons are quantum objects which can be transmitted very easily across. So, these are the physical qubits where any subatomic particle can be used. Typically, physical units can be any subatomic particle which can be used to represent a qubit. For quantum key distribution, a photon is a convenient choice because it can be transmitted very easily. That is the basic idea. The other kind of qubits that we have encountered, subatomic particles, they are generally localized in some way, in the sense that whatever is happening in one area that you are looking at, the subatomic particles interact and do things in a certain way. But transmission, which is the key part in this quantum key distribution, that would be preferred if you use a photon, and that is why photon is a convenient choice for quantum key distribution. Photons can be represented as electromagnetic waves, where the quantum phenomena is the part which will be utilized when we do our key distribution. So, a photon has a property called polarization, which is the plane in which the electric field is oscillating, right. So, we can use photons of different polarizations to represent quantum states. So, a photon with, say, having an angle or an oscillation in a certain way, which we call as our 0 degree, we can label that as state 0, and something which is 90 degrees to that state, we can represent it as 1. So, for example, if this is my 0, then 90 degrees to it is my state 1. Okay. So, that is the idea behind this definition, and we can use this principle that it can oscillate in one way versus the other way as one of the approaches to deciding our quantum state. So, once we use polarization as our basis of qubit or a quantum state, we need a device called a polarizer that will allow us to place a photon in a particular polarization. So, and there are things called Pockels cells which are going to allow only certain polarizations to go through, and it can be changed to the other kind based on applied field or voltages. That is the idea of a Pockels cell. That is a material, a crystal, which lets the light of a certain polarization to pass through under certain condition. If you change the voltage across the Pockels cell, then the polarization property of the light going through it can be changed. So, that is a very nice way of changing the polarization states that are going through a medium. So, this is our manipulator in some sense. It could be a static manipulator like a polarizer which just sits there and does its job, and the other one could be a dynamic one which is like a Pockels cell, which depending on the voltage applied will change the way the polarization is going to be on the other side. So, the polarization basis is the mapping we decide to use for a particular state, right. So, the simplest one that we are used to are the 0 and 90 case, which is our rectilinear axis geometry, for example, x and y, and the way we decide x, y kind of thing. That is our rectilinear, such that the angle across is going to be 90 degrees. The other option is to have a rotated case, which will be like a diagonal, such that once again the angles are going to be 90 degrees, all right, but they are with respect to a given frame can be rotated by 45 degrees. So, it could be either a diagonal case or a rectilinear case. So, since the photons are going to follow the laws of quantum mechanics, the complex numbers are added as opposed to their probabilities. That is one of the things which we have been learning as a part of quantum mechanics, right. So, when the additions are happening in the quantum world, the complex numbers come into the picture, but when we are observing it, it is the probability that we are observing. So, there are so here is an example as a result of this. We start at say point 0 and you can go to different places under different conditions, but the design of the property, if you are going to use this particular approach of propagation, will be such that there will be no photon at say 0.5, right. So, this is sort of known as annihilation operator that we are used to in quantum mechanics, that the phases are oppositely set such that the resultant can cancel each other, right. This can only happen because we are looking at their amplitudes and not their probabilities, because the probabilities will not cancel out ever. They will have no signs associated with it, but these will have. So, that is the idea. So, that was just an example. Now, in a realistic case, what are you going to do? In order to measure photons and their polarizations, one of the most important physical object is a calcite crystal. This can be used to recover the bits enclosed in a stream of photons. So, this is a non-centrosymmetric crystal. This is not a very uniform, optically it is not a 100% uniform crystal, it has a non-centrosymmetric geometry, and as a result of that, when light passes through it, it interacts along the diagonal axis and is able to allow one versus the other kind of the polarization coming through. That is the main principle out here, and in some sense therefore, it is a polarizer, right. So, what will happen? So, we can therefore correlate how they are going to go across and be present as we go along this calcite crystal. So, if all the 4 possibilities of a diagonal polarization exists, then as they go through it, they will switch into the cases that we will consider them to. So, for example, this diagonal axis of the calcite crystal will rotate 45 degrees to the incident polarization that we have. So, therefore, this particular one will come out in a direction which we have defined as 1. Okay. We defined 0 and 1, right, 1 coming out of the plane and 1 in the plane oscillating, that is how it was. So, this is a 2-dimensional representation of the actual thing. So, this one 45 degrees will give rise to 1, whereas the other one, because it is going to rotate only in one direction, the other one will end up producing a 0. Similarly, the other one, which is again at 90 degrees to it, will end up producing a 1 and vice versa, and so on and so forth. So, you can get a series of different zeros and ones in the plane that I am measuring, because I am going to always rotate as a result of the calcite crystal by 45 degrees to a given angle. That is the design. So, you can actually set up the problem by aligning the crystal with respect to the applied polarization to start with, so that once you define one polarization as 0, then as soon as you rotate the other one, the correspondence keeps on happening. That is the idea. Now, if instead of the case that I just mentioned to you, where we were able to do the process the way we have done it, if we have a wrong orientation, what will happen? That is the question. Then there is a 50% chance of getting the right answer. because 50% of time you will get the right answer and 50% of time you will not get the right answer, because there is always a 50-50 probability of getting one way versus the other, because there are only two possibilities in this kind of a case, right. We are either 0 or 1. So, if you get it wrong, it will be 50% wrong. If you get it right, it will be 50% right. Okay. So, in this design, the way it was we discussed it last time also, when we are going to send information across, it is like having Alice and Bob trying to send the information across, and there is an eavesdropper who is going to come in to try to see if the information can be stolen. That is the basic idea. So, what is the job of the quantum cryptographer? He or she has to prevent Eve from eavesdropping on communications between Alice and Bob. That is the idea. So, this is the famous problem which was first proposed and described well in quantum information theory by Bennett, Charles Bennett, and later on his associate Brassard, we will have the names again later on, added to the levels of cryptography that can be done, and so there are codes which go by their names. So, there are these two names. So, these are basically BB, okay, and they used certain number of parameters to do their things. So, there is this famous code called BB86 coding. So, it is Bennett and Brassard's, I think it is 1986 when they did it, and that is how it became the BB86, but we will go ahead and see how it is going. So, what are the steps? It requires, as we mentioned, quantum key distribution, which exploits the effects discussed in order to thwart the eavesdropper. If an eavesdropper uses the wrong polarization basis to measure the channel, the result of the measurement will be random. 50-50 means random, right. The protocols are important parameters here. A protocol is a set of rules governing the exchange of messages over a channel. Unless you set it up, you will have difficulty in getting to know how information transfer will happen. So, a security protocol is a special protocol designed to ensure security properties are met during the communications. There are three main, okay, it was not 84, 86, it is a BB84. There are three main security protocols for QKD, BB84, B92 and entanglement based QKD. So, we will only discuss BB84 here. So, that is the reason I introduced you earlier. I am sorry, this was 84. So, I will just correct it here. Okay. Okay. So, BB84 was the first security protocol implementing quantum key distribution. This uses the idea. So, as I mentioned, this is Charles H. Bennett and G. Brassard. It uses the idea of photon polarization. Okay. The key consists of bits that will be transmitted as photons. Okay. Each bit is encoded with a random polarization basis. Now, that is the main important thing, the random polarization basis. We will come to it in a moment. So, when there is no eavesdropping, how is it going to work? So, the sender Alice is going to send Bob the key. She begins with a random sequence of bits. Bits are encoded with a random basis and then sent to Bob. So, the basis can be something like plus, cross, cross, plus, cross. So, cross is 0, plus is 1, let us say. Now, accordingly, you will get your coding done in a certain way for the photons, and you get this kind of a resultant. Okay. Now, when Bob receives the photons and must decode them using a random basis, some of his measurements are only going to be correct. Why? Because there is a possibility of getting them correctly, and he uses a basis in which, let us say, one of his bases does not match up with what was used by Alice. And so, instead of getting the right numbers, there was a place where the right number did not come through. So, some are correct, some are not. So, then what happens? Alice and Bob talk on the telephone, because there are no eavesdroppers. So, we do not need to worry about this. Alice chooses a subset of the bits, the test bits, and reveals which basis she used to encode them to Bob, right. So, this is basically handshaking, this is the beginning part, you are testing it out. So, Bob tells Alice which basis he used to decode the same bits. Where the same basis was used, Alice tells Bob what bits he ought to have got, right. So, this is like they are checking their results on whatever they have done and trying to find out what went through, what was going on. So, when they do the comparing of the measurements, they find that two of the bases of all the set that was used were correct, were matching. So, they call that as test bit, right. So, once this test bit is established, then Alice and Bob can actually exchange information in where the test bits are included to be able to test if the channel is secure. Because if somebody tampers with this message, the parts which are not in the test bit, it does not matter, because that is not going to actually affect anything. But once you keep on sending the information, somewhere along the line the test bit will also be having an effect, right. So, if that happens, then they know that the channel is corrupted, otherwise it is secure. So, where is the trick? As long as no errors and no eavesdropping has occurred, the test bits should agree every time. Alice and Bob have now made sure that the channel is secure. The test bits are removed. Alice tells Bob the basis she used for the other bits, and they are both have a common set of bits, the final key. Okay. Now, you can actually imagine this iterative process going on for a very long time, such that you can actually send across a 256 bit key. Imagine what will happen, how long will it take to do all of this, but that is one possibility. You can do it step by step to see what happens. So, for example, here with this particular set, how do you get the final key? What you have to do is you have gotten this region where the test bits were there, you discard them, and what you find then is that there were these two which still matched, in spite of the fact that they were not using them as their test bits, still they match. So, they considered that as their final key. So, even if somebody is actually sitting there trying to figure out what is the secure channel, they will end up getting this, which is the discussion bits, the test bits, as the secure channel, as that is what they have been discussing. So, in other words, the phone conversation is classical, for example. So, somebody manages to hear the phone conversation. So, they will focus on getting this as the answer, right, because that is the discussion point they had, the test bits. But they really do not use the test bits, they discard it and then look for the ones where the thing worked, and that they consider as their final key. Okay. Now, this is without having any eavesdropper. with the assumption that when everything happened, ideally there was nobody who was listening. So, they went through the exercise as if there was going to be something happening, but nothing was there, and so they were able to get their answers very easily. Had it been that there was an eavesdropping, what would have happened? So, if say Eve is there as an eavesdropper and is trying to tap the channel, this will automatically show up on Bob's measurement. In those cases where Alice and Bob have used the same basis, Bob is likely to obtain an incorrect measurement. Eve's measurements are bound to affect the states of the photon, and that is the beauty of the quantum part here. Had it been classical, this was not going to be reflected, because in a classical system you can always take a little bit out and nothing happens, right. But in a quantum system, that is what we have learnt all this time, any kind of a perturbation or a change, or as we call it measurement, which is interaction, is going to affect whatever is left. And that is the reason the places where they were having their correct match is now going to have an incorrectness, and that is how they will immediately know that there was an eavesdropping. So, the advantage therefore is that the quantum gates allow us to manipulate quantum states without measuring them. That is the first thing, which is very important, because that is the basic principle behind quantum gates. So, this is actually, I do not know if I mentioned it before, but this is something which will have to be always focusing on, that the reason for having quantum gates is that we will be able to manipulate the quantum states without measuring them. Okay, so, the definition of a quantum gate is right there, and that is why they are sometimes very difficult to come up with. Quantum states cannot be cloned. Now, that is again one of the things which we know as it is a property of quantum mechanics. Teleportation allows a quantum state to be recreated by exchanging only 2 bits of a classical information. Now, this is the part which is very important. So, at the end of the day, what happened was they only exchange 2 bits, which was their test bits, to be able to know what was going on with the entire information transfer process. They did not use anything else. Okay. Quantum coin flipping is more fun than the classical coin. Okay, well, there are many other aspects of quantum information processing, and one of them is also quantum coin flipping, because that has much more probability than doing a classical coin flipping, and that is how it can be more fun than the classical coin flipping. But I do not know whether I will be doing that next or not. Let me see. Yeah, we are doing that next. Okay. So, before I go there, let me actually just do a quick review on what was the main process here in terms of quantum information processing. So, this part of the presentation or the classes that we have done has focused more on the quantum information processing, right. You have to understand one very important part of quantum computing per se, that this quantum computing heavily relies heavily on quantum information. So, you cannot have quantum computing or anything to do close to it unless you have quantum information processing done in the right way. And information processing or quantum information processing is some very important place where photons or light plays a very important role, because they are the ones which can be transmitted across much more easily than anything else. Any other quantum or qubit that you can think of, photons are the best in terms of transferring, and therefore, quantum information will almost always have photons as a part of its study. So, this is one thing which we have done. We basically studied this. Now, to make things a little bit more friendly, let us say, we will be looking at the quantum coin flipping kind of a situation. There is this entire area which is known as quantum games, and it is definitely a lot more interesting to do a quantum game versus the regular game, because it is a matter of chance, right? And you know that matter of chance is much better off with the quantum systems than with the classical systems, right? So, that is why it is the much more interesting case. So, what do we mean by quantum coin flipping? So, the quantum coin flipping principle is based on the following game. So, this is again this Alice and Bob kind of an idea. Alice places a coin head upwards in a box. Alice and Bob then take turns to optionally turn the coin over without looking at it. Now, that is the key part. If you look at it, then it has become classical information. You cannot do that. At the end of the game, the box is opened and Bob wins if the coin is head upwards, otherwise Alice wins. In the quantum version of the game, the coin is a quantum state. So, when we say head or tails, these are classical, but if I say H state and T state, then it is a quantum system. Now, for those of you who might be thinking that why is this so exciting, because this is related to your security in terms of teller machines, banking. Okay, so we will come to that. So, quantum coin flipping. So, in this case, let us formalize it in a slightly more rigorous fashion. Let us say that Alice can only perform a flipping operation, that is a gate which is sigma x. We know that the sigma x just does a flip. So, what does sigma x do? It takes the superposition and puts them in the opposite order. So, the alpha becomes associated with 1 and the beta becomes associated with 0, right? It just flip. There is a strategy that allows Bob to win always. He must perform Hadamard operations. So, now that is a very interesting principle. So, this means that if you do it in this fashion, there is a strategy which can be used by Bob which will make him always win if he does that. So, thus Bob places the strategy of the coins in a superposition of heads and tails, okay, because in order to get to the Hadamard operations, you need to have a superposition of the two states. So, I think we have gone through cases where we have discussed before that there were some gates, some processes, some discussions or quantum principles which allowed us to make superposition states. They are actually very important. There are some recent work that we have also done in terms of research where we have actually shown that creating superposition states are possible, say in optical qubits and things like that, and they are very important because that is one of the principles of Hadamard gates. And Hadamard gates or Hadamard operations not just appear in only these cases, they appear in almost everywhere. You will also find that they appear in Grover's algorithm, and they are often there in even in parts of doing the the Shor's algorithm. So, let us see what do we do here. So, here in this coin flip experiments, what you have to do is you have the Bob who is going to do his Hadamard operations on the original state. Alice is going to do a flip, and once again Bob does a Hadamard to find out what the original state was. So, if he keeps on, so that is what I was just saying, that if Bob keeps on doing Hadamard, he finally always wins, because the flip character will be always seen correctly by Bob every time he does a flip. Alright, so that is one part. The next very important thing which I mentioned, which is again a difficult one, is the cloning, right, because these are the things which we have to be looking at over and over again, because these are the places which are otherwise very difficult to do in a quantum system. So, the idea of a quantum or a qubit cloning circuit is very important. So, why are we doing all this? We are doing it because these are essential steps towards providing a full quantum teleportation circuitry. So, we will find it out later that all these different steps that we are doing, say for example, the quantum coin flipping that we just did, is one of the steps that is always necessary when we are finally going to do our quantum teleportation process. So, this is one phase. The other important thing we need to do in this connection is to actually have a cloning. So, how do you do cloning? We have perhaps visited it once before, but let us do it once more in this context because we would need it. So, a qubit cloning circuit is something which you need, which we know that it is very difficult to get otherwise, because in quantum mechanics you cannot clone anything. But we know, for example, in classical case you can always do that. For instance, by using a reversible XOR gate, it is possible to copy a classical bit. By using the same analogy, because it is a reversible case in case of classical, we should be able to do the same in the classical. And so, here we are looking at it, can we build a quantum circuit that performs with this kind of a situation with qubits? Is it possible? So, what is the idea? A qubit cloning circuit would therefore be meaning that we will have to do something which will be utilizing one principle or the other. So, if you take pure states, then it is possible to do such things, right. However, if you have states which are superposition states, then it is not that simple. What you will have is you will end up producing entangled states, right. So, in order to actually clone all the time, it is not possible to just say that okay, I will just use the same principles that have been used in a reversible classical system. It is not true. So, the reason I wanted to make this point clear here is that many a times you may think that if I take a perfect reversible classical computer, I should be able to do the same now, take it and just map it into my quantum computer, map it into the quantum world and I get a quantum computer. It is not going to happen, it is not that way. So, a direct mapping is not the idea between classical and quantum, something more is necessary. The idea is correct, it is somewhere there, but it is not exact. So, we have to do something more. What is it? So, in this case, for example, first statement is it is impossible to clone a qubit, that we know, there is nothing new about it. But there is a way to do this in a slightly different way. But we should note that when we take any two states which are superposition states, we will be getting terms which we just discussed, which were entangled. That is because in quantum systems, alpha beta is not equal to beta alpha, that is typically the case, right. You cannot just, because most of them, most of the time they are also complex numbers, and so complex numbers are not going to be often looking like this. So, in that case you have to do something more than that, and Hadamard gates again become very important. So, in this connection let us actually look at the Bell state circuit. Now, we have encountered Bell states beforehand, where we had taken states and put them together, and we found out that these Bell states cannot be separated back down to the individual states. That was the basic idea. So, we have just seen the similar condition here, we ended up producing entangled states. So, if you take this kind of a circuit, what you will end up producing, depending on how you have your the input states, the output will essentially form the entire Bell state situation. So, just a simple Hadamard along with the C0 gate will end up producing the Bell states that you need. So, this is a Bell state circuit. So, here is an example how it goes. So, you have the original you start with the same state, one of them goes through an Hadamard. So, it becomes a superposition state, it is going to the C0 producing the Bell state. Yeah. So, this is my Bell state then. In order to get to your quantum teleportation circuit, all of this that we discussed as of now are necessary. Why? Okay, by the way, I should mention that this symbol represents measurement. Whenever we have a symbol which sort of shows a meter of some sort, it means we are looking at a measurement point. Okay. So, what is it that we are doing now? We are actually having one state, say for example, a particular psi wave function is being put through a control knot with control bits which are of certain kind, which is going to go through this system where one of the cases can be a measurement case, but the other case we are not measuring. If you measure in the other case, then we are in trouble. We are only measuring one part of it. So, these are my measurements M1 and M2, and if you remember, we are always saying that we will be using 2 qubits on the classical channel, which is the case where you have allowed the measurements to happen, but the other one, which was my quantum case, remained as it is. It just got some kind of a mixture, or it got sort of impacted by these other states to finally give rise to the state that is of use. So, we will look at it in a slightly more different way. So, at each point how does it look? So, here as we enter, so this is another way of, so whenever we write down circuits, at every point when we look at it, we kind of put a circle and then we represent what we are seeing right there. So, my psi naught is a resultant of the interaction which is happening at this point of my circuit, right. So, this is how I look at it, this is how it looks. Okay. Now, what happens when I go to this point? So, this is how the second point would look like. One of them is going through the C0, the other one is already as we had seen before. So, this part now is going to go through a C0 on the one part. So, this part is going to go through a C0, this part we have already computed. So, when we apply that, we get this. So, this is how it looks like here. Now, at next one we will be having a Hadamard on one of them, and so when I apply the Hadamard after this point, then this is my resultant, and then you will be measuring, and you will be measuring these, which are basically the Bell states, right, between 2 qubits. Actually, these are basically the 2 qubits, different possibilities of the 2 qubits being measured. Now, that measurement is essentially what Alice has done at her end, right. So, that measurement is essentially what Alice has done at her end, because she prepared her condition there. This is how she prepared the states. She measured before sending it out, and she got these conditions, and as a result of that, when it is going to be looked at by Bob, then Bob's qubit state will be of one of the kinds, and when Bob applies any of these states, then he will be getting this particular state generated, which is the psi state, the wave function. So, what have we achieved as a result of all this? The teleportation process makes it possible to reproduce a qubit in a different location. Okay, let us look back. So, the qubit started off here, which was my psi function, which was this original state, right. Then see that was my psi. Psi was superposition of 0 and 1 with alpha and beta. Then I went through this circuit and I looked at every possibility right there. And when the final measurement was done by Alice, correspondingly what Bob got as a result of applying these gates is the same state which Alice had. So, what is the result? The teleportation process makes it possible to reproduce. So, we started off by saying you cannot clone the quantum state, right? That was the basic idea. But we ended up managing to do that by using this teleportation process, and that is why it is teleportation. It is not cloning, but teleportation, because it is not at the same location, right. And the original qubits are destroyed, because once Alice has done this, the measurements are done, those qubits are no longer there. So, that is the reason why we have to make this statement that the original qubits are destroyed. The next topic is on quantum parallelism and Deutsch quantum algorithm, which we will do in the next class. But before going there, I think what we did today is extremely important. So, I am going to once more revise this once more, because now we have seen the whole thing. So, we should be able to understand it a little bit better than we were when we were doing it by steps. So, let me actually go back on this a little bit to make sure that we understand, because we did the steps without originally understanding why we wanted to do those steps. Now that we have seen how this has all happened, we are going to do this once more in a little bit fast manner, but just see. So, essentially there was a lot of background which we have already done to just show that they have analogues in other information processing. So, the quantum coin flipping was, for example, an analog. So, you can use this in terms of some games and other things, but this was a step in the process of quantum teleportation. Please remember that. So, it was not like we were trying to play games or anything here. It is true that there is a huge area of quantum game theory. It is there nowadays. It is very interesting, and you can even think in terms of quantum casinos and discuss about those things. We can have discussions on all of that. But the basic original problem was that you have an eavesdropper and you are wanting to have a secure channel between two individuals who are going to transmit information. And if it is a quantum information, what we claimed was that it will be 100% secure. How is that going to happen? So, in this regard, we went through all the steps which showed how this is possible. So, and we used photons in this case preferentially, because photons are much better in terms of transmission of information in quantum sense. So, we used quantum photons, and photons have very convenient two states, polarization of one kind versus the other kind. We used that, and we made a parallel with the classical two bit system, and we use that as an information bit to exchange. And in this we also explored the possibilities of something like a quantum coin flip, and we found out that we could use that principle to understand how Alice can make the measurement or can set up the problem, which can be always recovered by Bob with 100% outcome, which is very important. Had it been not that way, then this entire exercise would have stopped right there. We did not want to do it that way, we wanted it that way. So, we found out how the coin flipping principles are. Once we understood that, we put it through in a circuit fashion, and we asked the question as to whether it is possible to clone, which definitely is not possible, because we know that in a classical system it is possible, but in a quantum system it is not. But in some sense we realized that this teleportation business might have something to do with this in that connection. And we started asking the question, where we landed up with the idea that in very simple cases it is possible that you can use simple control NOT gates to get to the principles that you are able to perhaps get back the same system, but that is true only if you use pure states or single states to start with. But if you are starting with a combination state, 0 and 1 being combined in some percentage order, which is how a typical quantum state is, then you always end up getting entangled states. You will not be able to get the individual states in the right order as you have started. And so, the principle of cloning, that it cannot be done in reality, survives, which is required for a quantum system, and that is the security, by the way, right. So, then what we, so we basically proved the fact of the principle, and it was important because that makes it secure. So, that is our secure, it is very important, right. So, then once we went there, then we started to ask or re-explore the idea that we have already talked about before, is the idea of the Bell states, which we know we have discussed in terms of entanglements earlier. The two state systems are always Bell entangled, that is what you get, they are highly entangled system. And since we are using polarization, it is always going to be two states. So, we did that and we found out that this always works out, because all you need to do is for the two states, you just add an Hadamard, you always produce the Bell states. Once you have gotten to that point, then you got one part of the circuit taken care, and once you did this, then you are able to get your final answer such that you can always produce a pair connected properly in this way. This is a Bell pair again that you are generating. So, then we are ready for our full quantum teleportation circuit, where the criticality is we have a measurement part associated, because Alice actually makes the measurement, and based on these measurements they are able to compare and understand what is going on, right. So, you go through in a circuit like this. So, we also learned this is very important, that whenever we write down a quantum circuit like this, there are points, and at each point we can write out how they are going to go by in this process, and then at every point when we do that. So, for example, we looked at the first point, then we went to the next point, then we went to the next point. So, at every point of applying a gate, we looked at what we were left with or what we were generating, and we were able to go through these and finally get to the point where the measurement was made by Alice, and correspondingly whatever Bob applied on his side as a gate, that is what we applied, and once we did that, we were able to get back the state that Alice had started with, right. Whatever Alice measured is not the state which Alice started with, please remember that, that is very important. She ended up making something which was possible to be applied a certain way of gates to get the original state, that was done by Bob. So, finally, as a result of this entire process, we were able to do a teleportation where we reproduce the qubit at a different location, and we maintain quantum mechanical principles in the right way, because the original state was destroyed. Okay. With this, let us end here. We will take up the next topic in the next class. Thank you.